let's try to get some geometric sense of how all of these ideas surrounding linear transformations fit together. So here I have a matrix defining a linear transformation. So this matrix is 3 by 2. That means its domain space is R2 and its range space is R3. So on the left here we have a copy of R2. That's just the XY plane. And on the right we have a copy of R3. So that's 3 space. Okay, the way I have this set up is that this matrix, or this linear transformation, the linear transformation represented by this matrix, transports this first vector v1 to this vector over here, and the second vector v2 to this vector right here. Okay, so since v1 is currently the vector 1, 0, we know that, right, it's the first standard basis vector. We know that if you multiply a matrix, if you multiply the first standard basis vector by a matrix, you just get the first column of that matrix. So you can see that the first column of this matrix actually just matches the coordinates of this vector down here. And then same thing for the second standard basis vector. It's 0, 1, and when we multiply the vector, this matrix by 0, 1, we get just the second column of this matrix. And look, the second column of this matrix is indeed this second vector over in 3 space. So think of this linear transformation as something that transports us from R2 to R3. And it does it in a way so that v1 gets transported to this vector down here, and v2 gets transported to this second vector up here. Of course, it doesn't transport us just in any way. It does it. This linear transformation transports us from R2 to R3 so that it follows the linear transformation property. And that means any linear combination of v1 and v2 gets sent to the same linear combination of these two output vectors. So to see how that works, let's get a linear combination of v1 and v2. So here I've creatively named it v right here. And you can see v1, or v is a linear combination of v1 and v2, right? v1 and v2 span R2, so v has to be a linear combination of them. And so when we multiply v by this matrix, it produces some image vector over here in R3. And here's that image vector. So currently it's so long that we can't even see it, so let's zoom out a little bit. Now if we move this image vector, or if we move v, its image moves around in R3. If v is the same as R1, then the image is the same as the output vector for R1 right there. And if v is v2, then the image for v is the same as the image for v2, like that. But also, if we have a sum of v1 and v2, like this, right, now v is a sum of v1 and v2, the resulting image over here is the image for v1 plus the image for v2. Right? So it's in this sense that this way of transporting from R2 to R3 follows the linear transformation property. Okay, so all that said, I think I'm going to hide these labels just to declutter this picture a little bit. Okay, now as we move this vector v around, right, one of the things that we've defined for linear transformations is the image of the linear transformation, and the image of the linear transformation is just all possible output vectors over here in R3. As we slide v around the plane, right, if we could slide the point v to every point in R2 and collected all of the resulting outputs over in R3, we would get the image. It's a little hard to see in this diagram what that is because, well, first of all, because this is a 2D picture of a 3D thing. So if we set this copy of R3 spinning, it's a little easier to see what the 3D situation is. So you can see that as I move v around, it's not going everywhere in R3. It's kind of constrained. If we sort of look at this on the side, the image output vectors for v are constrained to some subset of R3. And that's what that subset is called the image, and in fact it's a subspace. And here is what the image looks like. It's that plane. Notice that the image is spanned by these two output vectors. Right? The image is always spanned by the images of the standard basis vectors. And let me slow this down a little bit. Oh, that stopped completely. There we go. As we move, if we move the vector v around, oh, there we go. If we move the vector v around R2, its image moves around the image subspace in R3. Okay. Now, this particular linear transformation, or the linear transformation determined by this matrix, has its null space is trivial. It's the only vector that this sends to, the only vector in R2 that this sends to the 0 vector in R3 is the 0 vector. You can see that no matter what direction we go, the image over in R3 is not the 0 vector. Of course, if we take v and move it down to 0, then the resulting image over in R3 is the 0 vector. But since the only vector in R2 that gets sent to the 0 vector in R3 is 0, that means that the null space of this linear transformation is 0, right? The trivial null space. And the image is this, this plane here. Now, because the null space of this linear transformation is trivial, it's just 0, that means that this linear transformation is 1-to-1. What that means is that this linear transformation takes R2 and it situates it in R3 somehow without squashing it down at all, right? Without flattening any dimensions down to 0. And you can see that that's the case because R2 looks like a plane, but the image looks like a plane. So let's contrast this to an example where the null space isn't just 0. So I have another one set up here. Okay. Let's set this thing spinning so we can sort of see what the 3D situation is. So this vector here, I don't know what that vector is. That shouldn't be showing right now. Which vector is that? That's W2. So this should be showing. Why is it showing? There. Now it's not showing. And for some reason this point is showing. Let's see if we can make that point disappear. Okay. So this particular matrix. Oh yes, there was something else I wanted to say about our trivial null space, our 1-to-1 example. So the way I have this set up, this basis of v1 and v2 gets sent to those two output vectors. So if we move this basis, these two output vectors will still be the same unless I change them. So the image will stay the same, but the matrix will be different because the basis of input vectors is different, right? So that didn't change the image. Notice that it did change v, right? Because how I have this set up is this image vector, mv over here, is our vector v times this matrix. Well, if I change the basis, this matrix changes, and if this matrix changes, then the image of v will change as well. So that's why you're seeing the image of v move over here. So the thing I'm trying to point out is that this basis, since I have this set up so that this basis gets sent to these two output vectors, if I change the basis, the matrix will change. Okay. So here is sort of the same situation, right? I have a basis, v1 and v2, except I have this set up so that v2 actually gets smashed down to 0. So if we take this vector v and we put it right on top of v2, you can see that it's actually a little hard to see, but if you keep your eye on the head of this vector that is the image of v, as I slide v towards v2, the image of v actually becomes 0. It shrinks down to nothing, right? So that's showing us that this vector v2 is in the null space of this linear transformation. Of course, the null space is a linear subspace, so any multiple of v2 is also in the null space. So if I stretch this vector v out to here, it's still a multiple of v2, and so over in R3, it's still producing, the linear transformation is still sending it to the 0 vector. So you can't really see it since it's 0 right now, but if we sort of move it to the side a little bit, there's the image. If we slide it back towards the null space, we get 0. Okay, so for all of these vectors along the null space, as I slide v along the null space, notice that all of these are getting sent to 0, right? As long as I stay on this dotted line for the null space, you won't see any image of v. As soon as I move off of the null space here, then the image of v is non-zero, right? So every vector that isn't in the null space, every vector v that isn't in the null space, gets sent to something non-zero over in R3. So in this case, in the domain space, R2, we have this subspace that's the null space. And in the range space, we have this subspace that's the image. Now, this image is one-dimensional. It's a line. And the null space is one-dimensional. And the rank nullity theorem says that the dimension of the null space plus the dimension of the range should add up to the number of dimensions in your domain space. So this is saying the one-dimensional null space and the one-dimensional image, 1 plus 1 is 2, and we started in R2. So that's the content of the rank nullity theorem.